So VSEPR theory is a theory that helps us to explain the shapes of molecules. We talked about Lewis theory and how the atoms are connected in a molecule. VSEPR theory talks about the shapes of the molecule. So VSEPR, I know that's not exactly how you'd pronounce that, but it's close enough. This stands for valence shell electron pair repulsion theory. And this is based on the idea that groups of electrons are going to repel each other. Okay, it's a very simple model for molecular shape, but it works pretty well. So what is an electron group? An electron group could be a lone pair of electrons. It could be a single bond, a double bond, a triple bond, or a single individual electron, as in a free radical. So when we're talking about electron groups, we're not talking about pairs of electrons. We're talking about a specific group of electrons. It's very important to understand that. We're going to be looking at repulsions between electron groups on interior atoms. The exterior, the terminal atoms, do not affect the shape at all. So here we have a very simple molecule. There's a central atom, and we have a single bond between the central atom and each of the three atoms around it. That is a bonding pair of electrons. One single bond is called an electron group. And so we have three electron groups around this central atom. They're going to arrange themselves in three-dimensional space to be as far away as possible from each other. Okay? It's a little bit like children in the minivan, right? Brothers or sisters, and they fight with each other, right? And so they're not going to sit next to each other in the corner of the back seat. They're going to get as far away as possible. And mom likes that because then you don't have, you're breathing on me, right? They repel each other. So preferred geometry is going to have a maximum separation of those electron groups. That's going to be more stable because it's a lower energy state. So let's look at beryllium dichloride. So the Lewis structure for this, and it's very important to be able to draw Lewis structures because that is the basis for this theory. We're going to look at the Lewis structure, and we've gone over how to do those, so I'm not going to spend a lot of time reviewing that. We look at the Lewis structure. Okay, beryllium violates the octet rule. It's one of those little guys, right? So we look at the structure, and we look at the central atom. We ask ourselves, how many electron groups are on that central atom? 2. There's a single bond here and a single bond there. That's 2 groups. So how would 2 things get away from each other? So making it a little more real, because I know your childhood was maybe a while ago and most of you are not parents yet. So think about your ex, okay? This person that just like broke your heart and you hate them now. So this is the earth, this is you, and this is your ex, right? Wherever your ex is, you would like to be as far away as possible. So how could you get the farthest away as possible? You'd be on opposite sides of the earth. Okay? So these 2 electron groups repel each other. They are repulsive. So they're going to get as far away as possible. So they'll be on opposite sides. So this gives us a bond angle, and the bond angle is the angle between this bond and the other bond, and that bond angle is 180 degrees. So when you have 2 electron groups, you have a bond angle of 180 degrees, and then when we look at the geometry, these make a line. So we decided to call that a linear geometry. We're not trying to be tricky here. And does this actually happen? Yes. This has been confirmed by observation. So that's 2 electron groups. What if we have 2 electron groups that are not single bonds? So carbon dioxide is an example of that. So, here's the Lewis structure for carbon dioxide. We've looked at this one before. Central atom is carbon. How many electron groups? 2. The double bonds count each... Me and my stupid pens. The double bonds count as a single group because these electrons are shared between the carbon and oxygen. They can't get away from each other. They're between the same 2 atoms. But this group can move away from that group. And so they're going to do the same thing. They're going to be on opposite sides. We're going to get a linear geometry. Remember, an electron group is not a pair of electrons. Single bond is one group. Double bond is one group. Triple bond is one group. Okay? So, boron trifluoride. Bless you. So, boron and fluoride. I don't want to put that one up here. And fluoride and fluoride. See, now she's gone. She's like ninja. Right? That's why I didn't notice her come in. Or were you guys purposely talking to me so that I wouldn't notice? You didn't notice either, yeah. Okay. So here we go. Boron trifluoride. Here is the Lewis structure. How many electron groups on the boron? You guys lose your ability to count? How many electron groups on the boron? 3, thank you. So how would 3 things get away from each other? They're going to separate as much as they can, and so they're going to get 120 degrees away from each other. Okay? Right? So this is called a trigonal planar geometry, because if you look at the overall shape, actually maybe I should use the fat one for this. What shape is that? A triangle. Now we're back in kindergarten, right? That's a triangle. So the maximum separation is 120 degrees. This is called a trigonal planar geometry because this triangle is flat. Okay? It's a plane, like a sheet of paper, it's flat. We can have a trigonal planar geometry with things other than 3 single bonds. We could have something like this, where we have 2 single bonds and a double bond. That's still 3 groups. 3 groups get away from each other in a trigonal planar geometry. What's a little bit different about this one is the angles aren't going to be quite equal, because this double bond is a little more repulsive than the single bonds. And so this single bond, looking at that double bond, is like, ew. And it looks at this one, it's like, I don't like you either, but you're not as awful as that one. So I'm going to squish just a tiny bit closer to you. So the bond angles will be slightly different, but the geometry is the same. So 4 groups, a little harder to visualize. We can use balloons to illustrate what's going on here. You take 2 balloons and you tie them together, and they're naturally going to make this shape, the linear geometry with 2 balloons. You put a 3rd balloon in there, it's going to form this trigonal planar geometry. The balloons are representing electron groups. They're not representing atoms. So when we have 4, you add the 4th balloon, and it's going to push these guys down a little bit. Do you want to actually see balloons with this? Yeah, okay. So we've got the 4 balloons. They make this tetrahedron. This is a tetrahedron. And so it's basically a trigonal pyramid, but we reserve that name for something else. So this is a tetrahedron. So that's a shape name that you're probably not familiar with. The bond angles in a tetrahedron are going to be 109.5 degrees. And that's the math that I don't quite understand. Hey guys. Yes, question in the back. You do need to know the 109.5 degrees. So linear is 180. That shouldn't be too hard. Trigonal planar is 120. Also not too hard. So this is the one weird one that you need to remember, 109.5. And that's some geometry that, I mean, I could look it up and figure it out, but a 3-dimensional sphere divided into 4, that's kind of hard to think about. So this is what happens in something like methane. So here's the Lewis structure for methane. The central atom has 4 groups. They happen to be single bonds here. So those 4 groups get away from each other by forming a tetrahedron. We draw them flat in the Lewis structure, but it's not flat. Okay, so we could take these balloons, hopefully they're not going to pop, and we could make them flat, but they don't like to stay that way. You mess them up, you bump them a little, and they pop back into the tetrahedron. Because they're too close together. When they're flat, they would have a bond angle here of 90 degrees. They don't like each other. They're repulsive. They're trying to get away. In a tetrahedron, they're going to have a larger bond angle, 109.5, and so that's better. Just stretching. What if you put a fifth group in there? So a fifth group is going to push those balloons a little closer together. So you add the fifth balloon in, and we get this shape. This is called a trigonal bipyramid because it's two triangular pyramids touching each other. So we have two different kinds of positions here. These are the axial groups, and so they form the axis. Those are the white balloons in my model. And then we've got the equatorial. And so these would be, if these were the North Pole and the South Pole of the Earth, then these three would be around the equator. And it's important to distinguish these because this is the one where not all the bond angles are the same. Here, between an axial and an equatorial group, the bond angle is 90 degrees. And between two equatorial groups, the bond angle is 120 degrees. You can't divide this equally. It just doesn't work out. So the degree here would be linear, right? And so it's like a combination of a linear with a trigonal planar. So it's called trigonal bipyramid because it's two pyramids. And then there's octahedral geometry. So you stick another one in here, and now you've got four around the middle, and one up and one down. But in this structure, all of the angles are 90 degrees. So we don't really talk about an axial and an equatorial because they're all 90-degree angles. So this is called an octahedral geometry because it's an octahedron. And sulfur hexafluoride is something that does this. Any questions? So you need to know the names and the bond angles for these shapes. That can seem a little overwhelming at first, but if you just think about, well, what would balloons do? What shapes would they make? It's really not that bad. So let's determine the molecular geometry of carbon tetrachloride. So the first thing we need to do is draw a Lewis structure. So we've got a carbon and 4 chlorines. Yeah, question? How does that exist? Okay, let's go back and look at that. How does this exist? Sulfur is in period 3, and so it can do the expanded octet thing.
So is
Yeah.
there anything in period 3?
Any element in period 3 can do an expanded octet. Or period 4, 5, 6, 7, anything that has d orbitals. Period 1 and period 2 don't have any d orbitals to expand into. So carbon tetrachloride, probably going to have the chlorines arranged around the carbon. The chlorines are more electronegative. And then if we put in the correct number of electrons, we end up with this. The Lewis structure is the starting point for VSEPR theory. Draw a correct Lewis structure, then look at the central atom and ask yourself, how many electron groups around the central atom? 4. So how do 4 balloons get away from each other? They make a tetrahedron. So this would be, again with that, this would be a tetrahedral geometry. Yes?
You know how oxygen always goes to, or helium, hydrogen always goes to oxygen? How would that look in
in liquid chemistry?
Well, we'll talk about that. We'll talk about water and the hydrogen-oxygen stuff. There's some lone pairs involved there, so that makes it a little different. Yeah.
Are we going to have to learn about the shape too? Oh.
Yeah, we are learning about the shapes right now. It's also helpful to learn how to draw these things. So tetrahedrals are challenging to draw. So if you're going to draw a representation of this, you can put 3 of them in a plane, but then the other 2 are going to be out of the plane. So these are going to be all in the plane of the screen, and then one's going to be sticking out in front, and one's going to be behind. So the dashed line means it's behind the screen, and the wedge means it's coming out at you.